Okay, guys, today we're going to learn about solving trig equations. So we've been simplifying and verifying with trig expressions and identities, and now we're going to solve equations using these functions. Okay, so some of this should feel familiar. We're going to use the formulas from that same formula chart and the unit circle. So keep those two things handy. You're going to need your unit circle and the formula chart. All right, so at the top of page 10, you can see the first problem says solve the equation for x, and we're just really trying to work our way back to that variable and figure out what number that is. So A says sine x equals 1/2. So that question basically is saying, hey, I know that the sine value is 1/2. Where is that happening? What angle is this, right? So I want that angle. And I can find this on the unit circle, right? Remember, sine is y on the unit circle. So where are we going to have a sine value that is equal to 1/2? So go ahead, take a second, look at your unit circle, find that 1/2 for me. And hopefully you came up with pi over 6 and 5 pi over 6. Now, those two solutions both have a sine of 1/2. And in this case, it is not restricted at all. I'm just saying, hey, aren't there some more solutions still? And you'd say, yeah, definitely there are more solutions. Remember, we could go around the circle more times. So let's think about how we could go around the circle more times. Well, to each of these, if I wrote plus the period times n. So remember, my period is 2 pi in this case, times n. 5 pi over 6 would give me 5 pi over 6 plus 2 pi n. All right. And so what am I saying by adding that 2 pi n to the end is that this pattern continues on indefinitely, either positive or negative, and I'm just going around the circle any number of times. All right. Remember, the 2 pi portion is the period of the sine function. Now, the first part of this might seem just like what we did previously. It's kind of like when we used sine inverse or arcsine to find values on the circle. You knew that, hey, I knew what the sine value was, and I was going to go find those two angles. The one extra thing that we've kind of added in there was this section about the period n, and the reason we add that is because we might have more than one rotation. So we always account for going around the circle more times. And in this case, we're just saying, yeah, absolutely. I could have pi over 6 and I could go around the circle any number of times, or 5 pi over 6 and go around the circle any number of times. Okay, let's take a look at problem B. So problem B is going to read tangent of x equals 3. Now, if we were to look at the unit circle and go calculate our tangent values out, we'd pretty quickly find out that, wait, I really don't have a tangent value that's equal to 3 on the unit circle. So how am I going to solve this? How can I figure this out? Well, sadly, we're stuck relying on a calculator for something like this when we don't have a real angle, or at least not one from the unit circle. We have no reference point, so we're just going to have to rely on a calculator. So to put this in a calculator, what we're going to do is we're actually going to solve it kind of like we did those right triangle problems. And we're going to go ahead and say that, wait, my x value is equal to tangent inverse of 3. And you should end up getting 1.249 radians. Okay, so I'm just going to note this is in radians. And we could have solved it in degrees. We can change it by multiplying by 180 over pi. But let's just leave it alone as radians. And let's take a look at kind of where this angle is. So the first thing is there is a tangent over here at this angle, 1.249 radians, that has a tangent of 3. Right? This is where tangent equals 3, and it is 1.249 radians. And that same angle is going to have a matching tangent on the other side, actually. Okay, and how would I find that one? How far apart are my blue and green angles? Take a second, let's think about that. I'm hoping that you came up with that they're 180 degrees apart, which is basically just going to be pi radians. So if we add pi, we'll get 4.391 also in radians. So we found two different solutions, and we're going to give them the same treatment that we had previously, right? Remember, I found two solutions on the first circle around, but what about the circle repeating itself as I keep making more and more revolutions? Okay, so same process, okay? We're going to just have our values, and we're going to go ahead and put that plus the period times n on there. So 1.249 plus, what's the period for tangent? Hopefully you remember that it is pi n, so plus pi times n here. And on this side, I'm going to have 4.391 plus pi n, okay? Remember, the formula for the tangent period is pi over b. And in this case, b was just 1, so we didn't have to mess around with that at all. Okay, if we just keep chugging along, let's take a look at C. So part C reads as 3 tangent squared of x equals 1. And there's just a lot going on here. I don't have the tangent by itself, so it's very difficult for me to just guess what that x value is going to be. No, I don't want to guess. So instead, let's work our way back and get tangent by itself. Okay, so what's going to be the first step? Let's start by dividing this 3 to the other side. And now I've got tangent squared of x equals 1/3. Now, I'm going to go ahead and break this tangent squared down as well. We'll take the square root of both sides. And tangent of x equals plus or minus square root 1 over square root 3. I just kind of split up those square roots. But notice, guys, I did make sure to put that plus or minus. When we take a square root, we have to be careful to make sure we do that. All right. We drew that square root, so we always add plus or minus. Now, this is going to be 1 over square root 3. And we're going to go ahead and rationalize that as well. And we're going to get root 3, root 3. And we should get square root 3 over 3. And it is plus or minus. Okay, so we're going to end up with some extra solutions here because of that plus or minus. So let's go to our circle and think, hey, where are we going to have plus or minus root 3 over 3 as our tangent values? So I'm hoping that you came up with pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Okay, these are the 4 angles where tangent is going to equal positive or negative root 3 over 3. And let's go ahead and add that plus pi n to the end of these. So pi over 6 plus pi n, 5 pi over 6 plus pi n, 7 pi over 6 plus pi n, and 11 pi over 6 plus pi n. And basically what we're doing is the first set of answers that we had come up with, these blue ones, are solutions from one trip around the circle, which means just that first cycle of the unit circle, or however you want to look at it. Now, the solutions that are in yellow, on the other hand, represent when you haven't limited your distance and you are working on general solutions, meaning that you could go around the circle once, twice, you could go forward or backward as many times as you wanted. Okay? Okay, so let's take a look at problem 2 now. And you can see it says solve 2 cosine 3t minus 1 equal to 0 on the interval from 0 to 2 pi. And the best way to think about that is I only care about answers that are specifically in between 0 and 2 pi. So basically, we get to skip that last step that we were having, that part where we were saying plus 2 pi n or plus pi n based on the period. So we're going to go ahead and start this problem off the same way we did that last problem with the tangent squared. We're going to go ahead and get cosine by itself. So we'll start by adding 1 to each side. And we've got 2 cosine 3t is equal to 1. And we'll divide by 2. And I've got cosine 3t equals 1/2. And you'll notice I haven't even brought up the fact that this said 3t. Instead of just being a single variable, it's got that 3 there. Now, this is where it's going to kick in. So first, we're going to go ahead and figure out this problem the same way that we have been doing. Okay, we've been saying, like, I'm going to go to the unit circle and find the solutions based on that. So where is cosine 1/2 on the unit circle? Take a second and look at your unit circle. So if you paused the video and looked at your unit circle, you should have come up with pi over 3 and 5 pi over 3. So now let's take this 3t into account. Okay, so how do we handle this 3t on the interval? Well, that 3t means we're actually going to not just go around the circle one time, but we'll end up going around the circle 3 times. So how am I going to get my solutions? Well, my first revolution had 2 solutions, okay? So my second revolution is going to have another 2 solutions. And how am I going to find those? Well, we're just going to go around the circle and we're going to go ahead and add 2 pi to this, okay? And if I add 2 pi to each of these, pi over 3 plus 2 pi, I'm going to get 7 pi over 3. And I'm going to get 11 pi over 3. So that's one more circle around. Let's go ahead and do it again. Add 2 pi again. And we're going to get 13 pi over 3 and 17 pi over 3. Okay, so, and now you can tell that in red, I've got the first circle. Then I have 2 more circles. So this is the second revolution, and this is the third revolution. Okay, and these values are all equal to 3t. Okay, and so finally, to actually get my normal value, my t value, I'm going to divide by 3 for all of these. Okay, and you should just note 3 times around the circle means 3 times the solutions. So normally on the circle, you can have 2 solutions in that first rotation, but since this was 3t, I have 2 times 3, 6 total solutions. And to get those final solutions, we're going to just divide this by 3, because again, this was 3t. Our final answer is going to be divided by 3. So let's take all of these numbers we've got, and we're going to divide them by 3. And you'll see there's a pretty easy pattern once we start doing this. The first answer I get from pi over 3 is going to become pi over 9. 5 pi over 3 is going to be 5 pi over 9. 7 pi over 9. 11 pi over 9. You're already starting to discover something here. 13 pi over 9. and 17 pi over 9. And these guys are my final solutions for this. Okay? So once again, we're saying, hey, for this 3t, I'm going 3 times around the circle, which is going to give me 6 solutions. For each revolution, I'm going to go ahead and add 2 pi. So I have my first 2 solutions that I got from the unit circle in red, and then I add 2 pi to them twice to find 2 new sets of solutions, giving me a total of 6 solutions. All right? Generically, you'll have 2. That 3 triples my number of solutions and gives me 6. Now, don't forget at the end, you have to divide by 3 because this was solving for 3t. And so after that, we'll have 6 different solutions for t, and those are going to be my values. Now, here's kind of an interesting thought. What if we were solving this and we didn't have an interval? Okay, so just an interesting thought point. Let's see what would be like if we didn't have an interval. All right, so same kind of thought process. We were at the point where we solved this 2 cosine 3t minus 1 equals 0. And when we solved this, we got cosine 3t equals 1/2. And the first 2 solutions that I knew were pi over 3 and 5 pi over 3. Now, the nice thing about this is if we were solving this without an interval, we can very simply get all the solutions in one go. So I'm going to go ahead and say, hey, look, here's pi over 3 plus 2 pi n, and 5 pi over 3 plus 2 pi n. We just have to remember that we solved for 3t here. So to finish this problem off, all I'm going to do is I'm going to take these two answers and I'm going to divide them by 3. And I'm going to end up dividing this whole statement by 3 and this whole statement by 3. Now you could go piece by piece. Pi over 3 divided by 3 gives you pi over 9 plus 2 pi n over 3. Okay, you can also write it as 2 pi over 3 times n. And we've also got 5 pi over 9 plus 2 pi n over 3. So this example, guys, I just went on a little bit of a tangent talking about without an interval solutions for something that has multiple answers like we did previously. Okay, so in this case, each of these is a set of solutions, and you can see it's based off of that first solution plus the period, but we have to make sure to divide both of them by that 3. Okay, now let's look at problem 4. It says cotangent x times cosine squared x equals 2 cotangent x. And they've given us an interval as well. Okay, this little piece at the end is the interval. So I want solutions from 0 to 2 pi. Again, that's my first revolution. Okay, so all solutions are only between 0 and 2 pi. Okay, and this is kind of an interesting problem. We've got nothing that really matches up, nothing to combine, and I have 2 different types of trig functions. So one suggestion, why don't we go ahead and get everything onto one side? So the easiest thing that comes to me is let's go ahead and just subtract this 2 cotangent x from each side. And we can't really combine anything, so I've got cotangent x cosine squared x minus 2 cotangent x equals 0. Well, at least I've got everything equal to 0 now, and I can work on everything on the left side. Now, I notice each of my terms has this cotangent x. So I'm going to just take a second and try to pull that out. We're going to do that by factoring out. So if you can, go ahead and factor out that cotangent x and see what you get. Cotangent x, and I've got cosine squared x left over there, and minus 2 inside, and that is going to be equal to 0. Okay. Now, individually, each of these factors can be equal to 0 and give us its own solutions. So for example, this first part, cotangent x, can be set equal to 0, and the second part, cosine squared of x minus 2, can be set equal to 0 as well. And we can work our way down through each of these pieces to get our solutions. So let's start with that first one, that cotangent x equals 0. So we can just go to the unit circle and we could hunt down some areas where cotangent x equals 0. If you're not sure, remember, this is the same place as where tangent is undefined. So this is going to be at pi over 2 and 3 pi over 2. Okay, now let's take a look at cosine. Cosine squared x minus 2. Let's go ahead and simplify this down further. Let's move this 2 to the other side. Cosine squared of x equals 2. And now what am I going to do? Let's take the square root. So if I square root each side, let's not forget about our plus and minus. And now we're thinking, hey, wait a minute. Is my cosine x going to be equal to plus or minus 2? Is that possible? No, that one actually doesn't give me any solutions. This number is too big, and it's not in the range for cosine because it is not between -1 and 1. So this is not going to be giving me any solutions from here. This side gave me two different solutions, pi over 2 and 3 pi over 2, and they are on my interval, so these are going to be my answers. Okay, so these are in the interval 0 to 2 pi. Okay, remember, in the interval means we don't add that plus pi or that plus 2 pi in notation. All right, moving forward on to number 5. It says find all possible solutions on the interval negative 2 pi to 2 pi. And the problem reads 2 sine squared x plus 3 cosine x minus 3. One kind of interesting thing is actually this interval. It's actually from negative 2 pi to 2 pi, which is actually 2 revolutions on the circle, right? One is negative from 0 to negative 2 pi, and from 0 to 2 pi is positive, okay? So one is a negative and one is positive, just in terms of the regions that they're in. So how many solutions do you think we're going to have? What happened when we were going more times around the circle? On the previous problem, you know that when we had that 3t, we ended up with 3 times the number of solutions. Well, these 2 revolutions are going to give me double the number of solutions here as well. So let's go ahead and solve this out. Interestingly enough, I've got both sine and cosine in this function, and our hint says maybe we should use the Pythagorean identity. Go ahead and look at that formula chart and figure out which one your Pythagorean identities will match up with this. I'm hoping that you found the identity that says sine squared x plus cosine squared of x equals to 1. Okay, and I see this sine squared, so I'm going to go ahead and just get sine squared by itself in this formula. So we'll move that cosine squared to the other side by subtracting it. And I'm going to end up with sine squared of x equals to 1 minus cosine squared of x. And I'm going to substitute that in for this sine squared x. So now I've got 2, 1 minus cosine squared of x plus 3x, or sorry, 3 cosine x minus 3 equal to 0. And I'm going to go ahead and distribute this 2 into this. So I've got 2 minus 2 cosine squared x plus 3 cosine x minus 3 equals 0. And let's just start combining down some of our terms. I can see that this 2 and this minus 3 are going to combine. Negative 2 cosine squared x plus 3 cosine x minus 1. And now I'm looking at this and I'm going, okay, somehow I'm going to need to break this down further. And it looks like a type of function we've seen before. This definitely looks like a quadratic. So I'm just going to pretend that these cosines are actually a different variable. Okay, so we're going to say substitute, and we'll just use x for cosine in this problem. Okay, and we're going to end up changing it back. So it's okay, whatever letter you want to use. You want to use x, y, a, b, u, w. Either way, it's fine. Negative 2x squared plus 3x minus 1 equals 0. And now I'm going to factor this, okay? So go back to some algebra notes if you need to, but remember, we're going to factor again. And by factoring this, we should end up with negative 2x plus 1 and x minus 1. Okay, and let's go ahead and rewrite this again and put back in the other pieces that we knew. We knew that x is actually cosine, so I've got negative 2 cosine x plus 1, and the second parentheses is cosine x minus 1. And remember, this was all equal to 0. Okay, so now we're in a position where we can solve this, and each individual piece is going to be equal to 0. So let's set up each one and get our solutions. I've got negative 2 cosine x plus 1 equals to 0. And I'm going to go ahead and start moving things around. Let's subtract 1. Negative 2 cosine x equals negative 1. Then we can divide each side by negative 2. And I'm going to get cosine x equals 1/2. Okay, the two negatives cancel each other out. Now let's think, what solutions do I get for that? We're going to say, hey, cosine is 1/2 on the unit circle twice. That is going to be at pi over 6 and 5 pi over 6. Okay, and if I were to go backwards and find my solutions for the negative portion, we're going to end up with negative 11 pi over 6 and negative 7 pi over 6. Okay, you may notice that each of these, to get the negative angle, I just ended up subtracting 2 pi. All right, you can add or subtract the period to find more solutions as long as you stay within the interval. Okay, so this kept me within the interval and I was able to find all 4 of these solutions. Now let's see the other ones that we get from that cosine x minus 1. So if we solve the second parentheses right here, we're going to get some new solutions. Cosine x minus 1 equals 0. Let's move that 1 over. Cosine x equals 1. And we're going to get two solutions for this again. We're going to have 0, and 2 pi. But there's actually also, let's find our next solutions the same way. We're just going to say subtract the period to find the negative one, so minus 2 pi. So I get negative 2 pi as a second solution, and this one is 0. But this one is kind of a repeat, so it doesn't really matter. Okay. All right, so my unique solutions currently 0, 2 pi, negative 2 pi, pi over 6, 5 pi over 6, 11 pi over 6, and 7 pi over 6. So my problem actually ended up with 7 different solutions. Okay, so the first 4 came from here, pi over 6, 5 pi over 6, negative 11 pi over 6, negative 7 pi over 6. Then from on the right-hand side, we had 0, 2 pi, and negative 2 pi. So all of these are the solutions within the interval negative 2 pi to 2 pi. And we find more solutions in the interval by adding or subtracting the period in order to fill in the rest of it. So the first circle is very easy. The first circle comes from the unit circle, and then we add or subtract the period to get more positive or more negative solutions. Okay. Okay. Problem 6. Cosine x plus 1 equals sine x. And we're talking about from 0 until 2 pi again. All right, so that is my interval. So I only want solutions in that section. And we're kind of stuck here because even if I moved things over, it's very difficult for me to say, hey, I can get my sines and cosines to somehow mesh together or cancel out so that I can solve this. And in this case, what we're going to do is we're actually going to have to square both sides, all right? And if I square both sides, you got to be careful to make sure we square the entire function like that, okay? So notice on the left-hand side, I made sure to put parentheses around the whole thing. And on the left-hand side, this is cosine x plus 1 times cosine x plus 1. And you have to remember that we're going to FOIL this out. All right. And when we start FOILing this out, cosine times cosine is cosine squared. We're going to get plus cosine, then another cosine, and plus 1 as my last number. All right. First, outside, inside, last. We've got that. Let's combine our like term in the middle. And we got cosine squared of x plus 2 cosine x plus 1. And that's actually equal to this piece right here, sine squared of x. Okay, so now at least I'm kind of rolling here. I've got cosine squared x plus 2 cosine x plus 1 equals sine squared x. And again, once I've got these as squares, I can use the Pythagorean identity to help me. And the basic Pythagorean identity that we've used a lot by this point is sine squared plus cosine squared, and it's equal to 1. All right, so what I'm going to do is, again, let's just get one of these by itself. I'm going to go ahead and just get sine by itself since it's already on one side. So let's move over this cosine squared x. And now I've got sine squared of x equals 1 minus cosine squared of x. And I'm just going to take that and plug it in for that sine squared. So we've got cosine squared of x plus 2 cosine x plus 1 equals 1 minus cosine squared of x. Let's go ahead and move everything to one side, and that way we'll be able to get something more like a solution. So let's subtract 1. These ones are going to cancel each other out. And I'm going to add cosine squared to each side. And I've got 2 cosine squared x plus 2 cosine x equals to 0. And I see some commonality between these two. What can I separate out or factor from here? My GCF, or greatest common factor, is going to be 2 cosine of x. Okay. Left inside, I'm going to have cosine x, and on the right one is plus 1. Okay. So when I took out a cosine, this left me with just a single cosine from this one and a 1 for this one. Remember, this is all equal to 0. So I can take each of these parentheses, and that section can be set equal to 0. And it's going to give me different solutions from each side. Cosine x plus 1 equals 0. And I'm going to go ahead and divide that 2 to the other side, and I'm just going to get that cosine x equals 0. And this one's pretty simple. We know that cosine is 0 at pi over 2 and at 3 pi over 2. Now, on the right, we can move this 1 over. Cosine of x equals -1. And there's only one place where cosine is going to be -1, and that's at pi. Okay. Now remember, this problem gave us an interval between 0 and 2 pi. So we're not going to have any generic answers. We're not going to do any of that 2 pi n. Now the only thing we need to watch out for is that we should kind of check our answers and make sure that they actually work. Because the problem is we squared, so we need to check for extraneous solutions. And how can I check for extraneous solutions? Well, if we go back to our original problem and plug in the numbers, we can see if that is actually going to give me an answer. Remember, extraneous solutions when plugged in would not give you the correct solution. Okay, so for example, cosine x plus 1 equals sine x. That was our problem initially. Okay, and if I plugged and checked each of these, I should get that this statement is true. So for example, let's just do pi over 2. So I've got cosine pi over 2 plus 1 equals sine pi over 2. And if I go to my unit circle, I can check this very simply. We're going to say, hey, cosine of pi over 2 is 0, plus 1 equals 1. And we can pretty much tell, yeah, that's true, that's correct, okay? We can do this with each of our solutions. So cosine 3 pi over 2 plus 1 equals sine 3 pi over 2. Hang on, so cosine of 3 pi over 2 is 0, plus 1 is equal to -1. Wait a minute, something seems wrong here. I'm going to get +1 is equal to -1. So this answer is no good to me. So this solution is extraneous. Okay, let's just check that last one. So we're going to go ahead and do same equation, and this time we're going to test pi. So we've got cosine of pi plus 1 equals sine of pi. So cosine of pi is going to be -1. We're going to add 1 to that, and we should get 0, which is sine of pi. And we can say, yeah, that's true as well. So my only answer that didn't work out was 3 pi over 2. Pi and pi over 2 both worked out as my solutions. All right, so that's checking for extraneous solutions. Remember, all you do is you go back, you plug in the answers that you got into the original equation. Now, the reason this happens, guys, why do we end up with extraneous answers? It happens when we square both sides, specifically because we might lose a negative sign somewhere. Because remember, when you square, sometimes signs cancel out. And canceled out signs lead us to extraneous solutions sometimes. So just take a second and check your work at the end by plugging those back in anytime you square both sides. Okay, guys, a couple final notes on solving trig equations. So solving means you're going to figure out what that x value is or whatever your variable is. And you should remember that our answers kind of come in two different forms. And the first one is kind of the interval form, and that's when they tell you, hey, your equation is limited to just this area, so all your solutions are in between those two numbers or in that interval. And as an alternative to that interval one, we have a general form of answers. And the general form is when your equation doesn't have any restrictions or limitations on it. And that's the time when you're going to see examples of something like pi over 2 plus 2 pi n, okay? And what this end piece signifies is that this repeats multiple times, and it is always the period times n. And guys, those two come up based on what the question asks you. So if you have a question that doesn't mention an interval, you know that you're just going to write your answer as a general form, and you have to acknowledge the fact that it repeats. And if it does come in an interval form, you know that you are only going to give your exact solutions that are within that zone. All right, I hope this video helped, guys. Make sure that you practice solving trig equations.